All right, good morning. So today, I don't really have any new announcement to make, the same as back on Monday. Your assignment number 1 on recursion will be released on the coming Monday. You have just a few more days for catching up the basics on recursion. So the rationale will be you guys will just get busier and busier when the term progresses. So you definitely want to take this opportunity to really review the recursion as much as you can, because you definitely need to rely on that a lot later. Okay, I cannot emphasize enough. And of course, in your upcoming written test number 1, I believe shortly before the reading week, we'll definitely test you on that. All right, you're gonna want to catch up and make use of my office hour. Right, it's not busy at the moment, so you can definitely talk to me if you want to go over any extra material. All right, for today, I want to start with this experiment. Let me just make the final remark which I made on Monday again. Based on what we can see from this statistical table over here, we try to increase the input size by 2 in each row over here. You can see this column here, the input size is doubled each time. It seems like repeat number 1 is substantially less efficient than repeat number 2 because it can take days for that to complete. However, what we're gonna introduce to you very soon today is the so-called asymptotic sense. Asymptotically speaking, meaning that if your input grows infinitely large, these two algorithms actually wouldn't matter so much. Doesn't matter which one you choose. Of course, practically, you may have to make some additional concern. But for this course, once we start talking about applying the asymptotic analysis, big O, to algorithm, you always have to think about asymptotically. Okay? And what you want to really note is over here, repeat number 1, repeat number 2. You can see the next slide, there is a diagram. Sorry. My slide's a little bit freezing. Beg your pardon? Okay, this diagram over here. These two plots over here are very typical linear functions, meaning that, remember what a linear function is. When you say y is equal to ax plus b, you have some constant factor for x, right? And also some constant to be added up. And these two functions are definitely linear. So asymptotically speaking, they will belong to the same family of function, right? That's something we'll talk about today. All right, before I conclude this experimental analysis, we want to see its shortcomings. It's definitely very handy for us to really draw some nice table, visualize it, and make some statistically sound arguments. That's good. But what about the disadvantages? That's something we'd like to see. At least there are 3 of them. So number 1, in order to really run the experiments, your code must be fully implemented without any compilation or type errors, and also maybe even without any logical errors. Otherwise, you're not really making a fair comparison. So there's some issue of this, because sometimes your goal may not be really to have a final product before you can make a judgment. Sometimes you might be thinking, okay, in order to implement this new task, I may choose algorithm number 1. I might choose algorithm number 2. I got 2 different ways to implement. But before I commit my decision of implementation, can I make a decision first beforehand? So that's really something the experimental approach cannot do for you. It requires you must implement both approaches, or the alternative first, before you can compare. So that's a great disadvantage for us. Right? So what we want instead is some high-level analysis, and possibly we don't really have to complete the implementation. So in this course, we're going to talk about, I think that's mentioned somewhere. Okay. So here I say high-level analysis. What kind of language are we going to use to really do such high-level description? So yeah, let me finish this, and then I'll get to you. So in some other sections, and possibly some other iterations for this course, the instructor might simply use the so-called pseudocode, which means it got very informal in terms of the notation when you write the algorithm. But I would suggest in this course, we stick to Java, because that's something you have to do in the programming assignments and your programming tests anyway. Of course, when you are only asked to write Java informally, well, we'll make it very explicit in the question itself. We can be a little bit more tolerant on the semicolon, maybe some minor stuff. That's what you will see when we talk about examples in the class, right? So what we really want is some high-level notation to specify the algorithm without some working code. Disadvantage number 2. It depends on which operating system or which runtime environments you're running for this particular experiment. Maybe you're running on a Mac, maybe you're running on a Windows machine, maybe you're running on a machine that's currently very busy, so it's very easy to freeze all the tasks, right? So you want to make sure you really compare, make some fair comparison about these two algorithms running in the exact same operating system setup. So both hardware and software must be compatible, okay? And the final drawback, when you try to do some statistical analysis, you have to make sure the inputs you actually have used to really test your algorithm, they must be reasonably complete, meaning that at least you must have already account for the worst case scenario. If you haven't, then your statistics might be overly optimistic, right? So you always got to keep that in mind. Right, so that's about the 3 shortcomings for the experimental analysis. And what we really want is, in the next slide, we want to sketch out a better solution in addition to this. But you guys ought to know how to do the experimental analysis, number 1. Number 2, what's its drawback? And we're going to see how to improve it. You had a question before. Go ahead.
Yeah.
Awesome. Good. Thank you. All right, the next slides, we're going to talk about how we can move beyond experimental analysis. We want to be able to make our judgment possibly just on paper, as a mathematician, more like. Let's see. A better approach is to analyze the efficiency, and we're focusing on the runtime analysis. And it's going to satisfy the following criteria. Let's see. It should allow us to calculate the relative efficiency. What we calculated in the experimental analysis was the elapsed time. It's some absolute value. For example, 5 seconds versus 10 seconds. 3 days versus maybe 235 seconds, something like that, right? It's absolute. What we really want is to have some relative efficiency. We want to be able to compare functions on the paper to see which function might be more efficient in some sense, but we'll see that. If we are able to do such relative efficiency, we are now independent of the actual running environments. We don't have to run the algorithm on the paper. We just got to execute or trace the program in our head. That's all we're going to do. And the next point, and that's what I just mentioned before. We want to use a high-level description. Some instructors like to use a pseudocode, but I found that it's way too informal. When you don't really get things formal, you can easily write something that you don't really know what you're saying, right? So what we really want is to get to Java code, even when we are doing some analysis. But we can have some tolerances. You will see what I mean. Sometimes we can ignore some brackets. Sometimes we can ignore some semicolon. That's OK. But what you write should really almost make sense for coding. And we want to consider all the possible inputs, especially the worst case scenario. We're going to do one example very thoroughly today to see an idea. Okay. And we'll learn a better approach, and there's going to be 3 things. Number 1, we have to know how to count the so-called primitive operations, like a simple operation. That's something to do first. Number 2, we want to know how to approximate the running time as a mathematical function. And the function takes as input the size of your maybe array or your collection, right? Input to your algorithm. Number 3, we want to focus more on the worst case scenario. Sometimes you don't necessarily have to see very detailed exactly how the algorithm actually works. Just by looking at the structure of the code, you will be able to figure out the running time quite accurately. Right? That's something we have to practice. Well, we've got lots of examples for you. If not today, definitely next Monday. Guys, any questions so far? Any question, any concern? Before we move on to number 1. I'm hoping to get as much as possible today. But we'll definitely finish the whole asymptotic analysis next Monday. But let's see how fast we can go. Interrupt me if you got any question. And I would suggest let's take attendance now, because I will rather we go more without a break for the coming topic. You can just get your iClicker ready. Meanwhile, just bear with me for 1 minute, okay? I'll just need to reset my location very quickly. Okay. So view the course online, and then there we go. And then I'm going to settings. I'll definitely try to save you time by doing this before the class whenever I can. Okay, let's go to settings, and then we go under attendance, right? So don't require, require, allowed, save. All right, so guys, get ready. So I'm going to start a class now, and then I'm going to start a poll. Okay, I'll take 30 seconds to get your check-in. If you got any issue right now, please come to the podium right away, all right? If you got any issue, you have to let me know right away, all right? Any issue, please raise your hand. At least I would know. Anyone? Okay, I'm going to stop the poll now, okay? Yes, yes, yeah. If you got issue, yeah, I'll let you sign up, okay? I'm just gonna stop it. Thank you, guys. So let's say we don't take a break. I will just sign up your classmate very quickly, and then we'll resume. I'll promise I'll give you a break in the middle. Yes, can you find your last name here? Okay, you may want to find out what the issue was, actually. Yeah.
I can't, my phone isn't compatible with
yeah, try to sort it out, please. Yeah, otherwise, you may not want to just do this every time. Yeah. All right, thank you. Alrighty, thank you, guys. So I promise I'll give you a break very soon. But I would suggest we go on to that particular example about counting primitive operation right away. Okay, let's do that. All right, counting primitive operations. Basically, you have to understand what it means to be a primitive operation, number one, and then we'll try to count very precisely on a particular algorithm. Let me go over some definition lists together with you, and then some of them might require a little bit of further explanation. Let's see. What's a primitive operation? It corresponds to a low-level instruction, like a very simple one. If you take your 2021, EECS2011, in that course, you learn about different machine instructions at the assembly level, at the machine level. So every one of them is the most primitive one. So you can kind of see some correspondence over here. But if you haven't taken 2021, that's okay. You don't need to worry. But the bottom line is you should know, every primitive operation will only take a constant execution time. Asymptotically, anything that's constant, it can be ignored without considering any further. Okay, that's something I can say. And the first one that's primitive will be variable assignments. Whenever you do x assigned to 5, right? That's obvious. And if you want to go indexing into an array, AI, right? That means I want to, for example, I could be some integer expression. I just want to go to this particular location for the array. For this course, always remember, whenever you want to go to some arbitrary index or location in an array, it always takes constant time. It's a primitive operation. It's very efficient. And this insight over here is going to impact how we do further analysis about the array versus linked list. We'll get there later. But for now, just remember, indexing into the array is a primitive operation. And if you take your 2031, your professor will explain to you, this particular integer value I will be somehow translated into some offset of the address. So you can go to the starting address of the array and go to that corresponding location. Calculating the address is a primitive operation. So that's why AI is also a primitive operation. Okay, very quick. The next one, any arithmetic, relational, and logical operation, you might be thinking, how about bitwise operator? It's also primitive, but I didn't include it here. We don't really use it in this course. All right? Arithmetic, relational, logical operation, they're all primitive, okay? And this one's interesting. Since we talk about object-oriented programming, so this one is specific to that paradigm. If you want to get access to an attributes of an object, let me show this to you. Okay, so we talk about accessing and objects attributes. Right? Let's say this. Let's make it very precise. Let's say we have, let's say, person. P will be new person. Right? You may pass an argument value over here. Right? So P is now a reference type. Right? If I say P dot spouse, for example. So let me visualize that a little bit for you. Let's say P over here is pointing to some object memory block for the objects of type person. Let's make the assumption that we only got two attributes for the person objects. We got age, integer, and also spouse, which is just another person, right? So I presume you guys are quite okay with such declaration for the attributes. If you're not, you may want to speak to me, all right? You definitely need that too in your programming test. So let's say we got age, and also we got spouse. So the age could be some value 23 over here. Let me start with something simple, all right? You might do, for example, p.age, and the dot notation, just to remind you, involves about looking up the address of the reference that is stored in P in the memory, okay? To look up the address that is stored in P. And whenever you want to just look up something, constant. Or we say primitive operation. When I say PO in this course, I really meant primitive operation, okay? So if I just want to call p.h, looking up what's really stored in over here, I'm going to go to that particular object and access h. So this is a primitive operation, right? In OOP, you may actually have to do multiple dots, right, to really get somewhere. Let me give you one example right away. Let's say we got P here. What about we got another object called Q? And Q is just another person, and by some very simple setup, I'll leave the programming part to you. Let's say we got another person over here, and let's say we also got age, maybe 25, doesn't matter. Okay, let's say P and Q, they are married to each other, right? How do we visualize it? Quite easy, right? You can say P.spouse is set to Q. Q.spouse is set to P, right? That makes sense, right? Now, if I want to find out, for example, the age of the spouse of P, how do I do that? I can say P dot spouse dot age. And of course, this kind of dot notation can really continue indefinitely as long as you need it. But the point is, even if you got multiple dots over here, it will still be considered as a constant time operation. So look up what's really in P, go to that memory location, look up what's in spouse, go to that memory location, and look up the age. You just got multiple lookup. As long as the number of lookup is constant, is finite, it will be considered as constant primitive operation. Okay? Multiple. So we got here, and we got here. Multiple lookups will still be primitive operation. Are we okay so far? In general, you may have as many dots as necessary if you got more classes that's involved. But I'm just giving you one example here. All right? That's correct. The number of dots over here, we assume in this course, doesn't really affect the fact that it's primitive operation. That's correct. It will be very weird if somehow the number of dots over here will depend on certain input size. It's not the case. If this has to be the case, I'll let you know explicitly. Yeah. Question?
So even though for being very pedantic about it, the more dots you have, the longer the execution time is going to be. Since we typically think of the efficiency as being in terms of the variable that we're looping over or the size of the input, that's not what we're
That's not what we, yeah, let me, very good question here. Let me try to phrase a little bit differently. Okay. Think about this, realistically. Let me put it down here. In practice, the number of dots used to inquire some attribute value does not depend on the input size. Usually they are very small. You might just be able to find this yourself as a self-observation once you get to maybe the software design course in the third year, 2311. You will see that even for a very substantial project you have to do, you don't normally have, for example, more than 3 or 4 dots. That's it. That's why in practice, it's definitely going to be constant. There's no concept about looping when you do dot notation. No. All right? No looping concept. All right? Constant. All right? All right, guys, if no question, let me move on. Okay, so that's about attribute access, right? It's good to clarify that. And it may just have a return statement over here to say, for the accessor, the method that returns something. You say, I want to return certain calculation result. And here, the result itself may involve certain operation, but let's say it's only a value that's already calculated. So that itself is a primitive operation. All right, now here's an important question. Maybe obvious to you. Is a method call a primitive operation? Ferris. Could be either. You want to elaborate a little bit more? When can it be primitive? When can it be not primitive? Go ahead. Yes. Absolutely, fantastic. Thank you so much. So I think I'm leaving this as a last item in the list. Is a method call a primitive operation in general? No. It may be, but it may be not. Really depends what you're calling. I'll try to visualize this a little bit because it does depend on the call structure. Okay, let me make it very explicit over here. Oh, sorry, wrong way. Over here. Method call. Okay, so let's say if I got some objects, the general structure is I got object dot method m with some argument value. That's the general structure, right? So here we got 2 cases. Case number 1. And the method that's being called contains primitive operations only. Primitive operations only. The structure would look like something like this. Think about this is this is the body of the method m. Let's say this is m. Let's not worry too much about whether it's accessor or mutator. You can think about you just got individual line, and each one of them does not involve any further method call. Or actually, it could. Okay, let me put it this way. I want to be very precise. Each line over here corresponds to a primitive operation. And now, I want to point out some common misunderstanding right away. Later on, I'm going to require you to say, I'll give you some piece of code in Java. You got to figure out the running time. For example, linear or quadratic, etc. However, some students, they like to look at the structure of the code in the following way. If you have a single loop, that means it's going to be linear. If you have a double nested loop, it's going to be n to the power of 2. I can tell you guys, it's not true in general. I'll give you guys a little bit more information later. Okay? Whenever you have a loop, it doesn't really mean your algorithm cannot be constant time. It could be, but it cannot be, right? Here, I just want to put some notes over here. Can be, number 1, a method call. Helper method call you can think of. And it can also be a loop. Having either of this can still make the method itself primitive operation, can still be. It really depends on the structure of the loop, all right? That's something I'll try to get more information to you later, a little bit later. These two may still be primitive operation, okay? And of course, for case number 2, obviously, M contains some non-primitive operation. I'll give you some example over here. Let's say M over here. Typically, you can make a method non-primitive by having either an expensive method call or having a loop in a particular way. I'll just give you one example of the loop. For example, you might have over here, let's say for integer I, let's say 0, I less than, let's say n. I'll explain what n is in a moment. Okay, you do something over here. And the n over here may be the size of some input array. Right? This will make this method here not primitive. It will be linear. And guys, what I just have said are not contradictory. Let me repeat again. Having a loop does not necessarily make your method non-primitive. It may or it may not. I haven't given you one example where it may not, it will make it still primitive. I'll give you that maybe later. But for now, this will be a typical structure of a loop where the bounds on the number of iterations over here depends on certain input size of a collection. That's a typical structure where it's non-primitive. Okay, let me say one more thing before I take your question. Another one would be, there might be another line over here, so this would be a method call that simply containing non-primitive operation. All right? So you really have to judge carefully. Yes, question. Yes, yeah. So that will be a little bit look ahead. If you look at this loop specifically, it's called a linear function. Yes, we're going to talk about it later.
For I equals 1 to n, if I modulo 2 is equal to 0 return, then that would be constant, right? Because it doesn't matter what n is. Every 2 integers, you're going to hit something that has modulo 2 0. So
let me go over that example maybe together with you, maybe offline first, before I talk about it. It's a little bit too much ahead of what we're talking about. Let's talk about it off class, all right? Yep. All right, guys, any questions so far about this principle here? A method call may or may not be primitive. That's the bottom line you want to take away. Now, in general, and then just some example for you. Like what Farrah said, it could be expensive method, like a sorting an array using bubble sort. That's just one example. All right, let's now do one exercise together. All right, and I want to do the first one very carefully and thoroughly with you. So what I want you to do is this. The same code over here on my iPad here. I want you guys to take 1 or 2 minutes, let's say 1 minute or so. Number one, I want you to take a look at the code to see what it is trying to do. Number one, it shouldn't be too surprising, easy one. Number two, I want you to think about these 2 questions over here. Number one, how many times will this I less than n operation be evaluated at a runtime? How many times precisely? Okay. Number two, how many times will the body of the loop, which is over here, be executed? That's question number 2. You want to be 100% correct on the answer. It cannot be one off, or it cannot be too small, too large. Got to be exactly the number. Okay, you guys, please take 1 minute to take a look. If you got an answer, hold it. That's okay. I want to give everybody an opportunity to think about. This is basically what you have to think about in the test and exam. All right? You got answer or? Oh, no, I don't want answer now. I don't want. You just question. For recursive method over there, it depends. You got to analyze the structure. We'll talk about it maybe a little later. Yeah. Mm-hmm. Okay, before I take any thoughts quickly, just back to your recursion problem, okay? So analyzing running time, what we will start with will be, we just try to analyze iterative algorithm to begin with. And later on, maybe after the reading week, when we talk about merge sort and quick sort and binary search, we'll show to you the best way to really figure out the running time for a recursive method. It's not to really just by looking at it line by line. Instead, you have to somehow do so-called unfolding of the recursive function mathematically. That's something I will show to you after the reading week. So for now, you can simply assume that when we give you some method to calculate its running time, it will be just iterative. It will not be recursive. Once we show to you, you will see that will be a much better approach to do it other way. Yeah. All right, guys, let's start. Okay, can I assume at least you guys are familiar with what each line would do, right? That's something I don't need to go line by line with you, okay? And one thing I want to note, in order to do the analysis to count, we don't necessarily have to understand exactly how the algorithm works. The algorithm itself may work or may not. Remember what I said before. When you want to judge to see if something should be chosen, you can just jot down certain informal sketch of the algorithm. So this could be one of them. All right? So now, question number 1. How many times will this particular expression be evaluated? I just want the answer. N, okay, ferrets, N. Any different answer? Anybody would think there should be N minus 1. You think there should be N minus 1? Very good. Okay, guys, I will try to either lead you or mislead you a little bit, okay, and then I'll see if you change your mind. It's very important to get this through, all right? Notice that the starting value here is 1. Starting from 1, 2, 3, all the way to up to n minus 1, we'll run the loop. After that, we terminate the loop. Shouldn't that be n minus 1? Will you guys change your answer? Who thinks that should be something other than n minus 1? Okay, somebody, okay. So ferrets, what would you think? Still n? That's exactly right. That's exactly right. Guys, the answer should be n. Why? Let's visualize that a little bit. The idea would be you want to think about this expression over here is going to be evaluated a certain number of times so that you can stay in the loop because it's true. But the final time when you exit from the loop, it's going to be evaluated to false. That's the very definition for looping, right? What's going to happen is like this. I value here, and I less than n. Think about what's going to happen. Iteration number 1 is going to be 1. I less than n will be true. And then 2 and also be true. All the way to when e gets to n minus 1 less than n will still be true. Finally, when we increment it to n, it will be false. You can see that we got all true evaluation over here for n minus 1 time. And we got false. This is telling us we should really exit from the loop. Be careful, all right? Any question about this? If you're struggling with this, talk to us, right? It's really important, all right? Yes?
I was just going to ask, so for example, if the loop terminal 0 and not 1, then would it be n plus 1?
Good question. Hypothetically, if I change this guy over here to be 0, yes. In that case, we're going to go from 0 all the way to n minus 1, which will be n times, plus the final time where is going to be false, so n plus 1. That's right. Very good. Yes. All right. So here, I would say this. I'll write it down here. So it's going to be n minus 1 time plus 1. So just for your notes, this is when I less than n evaluate to false. For the first n minus 1 time, is going to be I less than n evaluated to true. Right? So that you can see it. True and false. Okay? Question 1 is done. What about question 2? Should be very straightforward, right? How many times is the body of the loop going to be executed? N minus 1, n minus 2, n plus 1. What should that be? Should be n minus 1. That's exactly when the expression here evaluated to true, then you're going to execute the body of the loop, right? Again, we go for the very definition for while loop or for loop. N minus 1. And this one corresponds to the I less than n evaluated to true. Okay, I'm just preparing you guys for answering the question fully, right? I'll pause a little bit if you want to ask a question. Go ahead. It is actually. I'll tell you why. It's valid Java syntax, of course. It's I just kind of put the brackets sometimes in the same line just to save some space. It is. I'll tell you why. This if statement over here has the corresponding brackets like this.
Oh, no, I was talking about the increment. Like your increment.
You mean missing the semicolon?
No, you know like how we have far in I and then in, like increment usually goes there from what I've seen before. So.
Sorry, can you just say your question again? Are you saying that this wouldn't compile for what reason?
No, I'm asking would this compile in Java because the I++ is outside the.
No, it's in. Okay, let me explain. Yeah. First of all, are you guys convinced? This bracket over here belongs to the if. Yes. Good. And then this one here, which starts the loop body, corresponds to this. Yes. I++ is inside. So that's fine.
I think he was referring to because like usually we see for in I equals 1 colon I less than n colon I plus plus instead of having the I plus plus.
Oh, I see what you mean. Oh, guys, in case you got, okay, I see what you mean. Okay. Just in case you don't know, I don't mind mentioning that. Whenever you write for loop, right, there are 3 parts over here. 1 part here, 1 part over here, and 1 part over here. Okay? Agree? Okay. So let me just put some name over here. Let's say this will be initialization. I'll say I. Okay? Some assignment, for example, declaring I to be initialized to be 0. This will be some, I call it a state condition, the condition for you to stay in the loop. And this one here is called a progress, output P, how you can make a progress towards the termination of the loop. All right, that's how you learn for loop for the first time. Maybe your professor is too kind to let you know you should always write this way. But in reality, you can write differently. I'll show to you. Okay? This part over here may be moved out of the loop. This part over here may also be moved inside the loop, typically to the end. Over here. And what does that mean? That means the shortest for loop header you may write is something like this. For loop, nothing here, semicolon, put some condition here, semicolon, and do this. That's the shortest loop you can write. Depends on what you need.
The implementation isn't part of that progress when you put it like inside the loop at the end. Does it need a semicolon? Because in your text it doesn't have.
Yeah, I absolutely agree. So what you're saying is there should be a semicolon over here. That's what I really meant. So let's say in your exam or written test, if you're asked to write some Java code, we can be a little bit tolerant on the semicolon. That's not a problem. So sometimes for me, it's just easier to present, in the code, on the presentation. So, but of course, in programming tests, by all means, you gotta make sure it's valid. Absolutely. Question there. Absolutely. So for loop and while loop, for your information, they are completely equivalent in terms of their expressive power. Given an arbitrary for loop, it can convert it into while loop, and vice versa. Absolutely. Do you know what I mean? Do you want me to make it a little bit more visual for you? You understand? Okay. So guys, if you really got a little bit trouble with this, now is still the time to catch up, right? I really want you guys to really catch up with the expected pace for this course. No matter how, if you don't mind, shaky your foundation might be, right? This is now the time to catch up. Yes? Yes, absolutely. Yeah. Sorry guys, I didn't know this will bother you so much. What I will do for you guys, how about that? No problem. Anything that might bother you, which I can fix, I'll try. Go ahead. Absolutely. Let me just recap about question 1 answer very quickly. And guys, I think after either today or maybe next Monday, I'll give you one challenging exercise to practice. Okay, I promise, I'll give you. But let's now go back to question number 1 just once more. When we talk about how many times I less than n, think about I less than n over here is a state condition for the loop. The state condition tells you this. If it is true, it's going to stay in the loop. If it is false, you're going to exit from the loop. So basically, you're going to calculate how many times you will evaluate to true in order to stay, and how many times you will evaluate to false in order to exit. To exit, there's only one time when you evaluate to false. That's why you will see this one time over here. And now, how many times you're going to evaluate to true? It now depends on the initial value over here and all the way to this condition over here. Because you know, in order for I to be less than n, what will be the maximum value that will be evaluating the true? N minus 1. So that's why you'll go from 1 all the way to n minus 1. So that's why you have this part over here, n minus 1 plus 1. So that'll be n. All right? Guys, this was so important. All right? Later on, the exercise I'm going to give you, if I recall correctly, is a nested loop. So you're going to know how to calculate. All right? All right. If everything is good, so let me now do the following. We want to calculate precisely. Well, we haven't done yet, right? I just answered some foundational question for you. What we want to do now is to count how many primitive operations in total in this particular method or algorithm. What we need to do is go line by line. And you guys got a chance to practice what you just learned 10 minutes ago. Line number 1, let me highlight it. How many primitive operations do we have in just this single line? Anybody at the back? Oh, go ahead, please. You think that should be 2. Can you tell me which 2? Absolutely. Array indexing is 1. The variable assignment is also 1, so we got 2. I will put the 2 over here. And we're going to just do some simple add up at the end. And let's now do this loop header, which could be tricky if I didn't answer the 2 questions before, right? But now it should be better. Let's now take a look. This line. Now, how many primitive operations do we have? So now you want to take into consideration the answers to question 1 or question 2. I want just an answer. And if your answer is correct, I'm going to ask you to justify. Anybody at the back want to try? Otherwise, I'll choose your very passionate classmate at the front, which I really like. Go ahead, please. Yeah, I like your answer. Let me repeat it. You said it should be 2 because here is 1 variable assignments, but this is another 1, so it should be 2. It's not correct because you didn't really consider the fact that this loop header is actually going to be evaluated multiple times when you execute the code. But I'm glad you mentioned the answer because most likely some of your classmates might still make the same mistake. So it's good to point it out. Very good. Okay? Any other answer? Okay, I'll point somebody. Please, go ahead. N plus 1. Okay, that sounds promising. How did you figure? You're getting somewhere, but the explanation, if I heard you correctly, is not exactly what I'm looking for. But let me see. Okay, guys, thank you. I'll point you guys for the next one. Okay, let's see this. Number 1, you want to look at this one here. Now, Guys, how many times is this particular variable assignment, which will initialize I to be 1, how many times is it going to be executed? 1 time. That's why it's called initialization, right? 1 time. Don't get confused, just 1. Okay? This one here will just be 1. And this guy over here, as we just did, how many times is it going to be executed? N times, right? N minus 1 times for true, and 1 time for false. So what do we have? N plus 1. N plus 1. And if you want to make some notes yourself or when you watch the video, this one here is corresponding to the initialization. I'll try to see if I can make it a little bit more visual for you. The one here is corresponding to this variable assignment here. On the other hand, the n here is corresponding to I less than n, which we definitely talk about over here, right? N plus 1 in this case. Yes, question?
Misconception. I thought it would be 2n because I thought that every time the I would get updated, so it would be assigned to the
Good question. It depends on where you put the I++. If I put I++, let's say over here, which I could, in that case, you will calculate differently. It's a very good question. So guys, some exercise you may want to do for yourself, right? I'll wait for a little bit. And if you didn't really put the progress part over here, you don't really include it. You only calculate what you see. Instead, you can try to move this I++ into over here. Number 1, I bet you, the overall answer will still be the same. But your steps of calculation may have to be modified a little bit. That will be some exercise I suggest you do. All right? Question?
Why isn't the for operation considered in addition to
Sorry, which one?
the for loop, right? So
Uh-huh.
you have a keyword for, and then we have conditions within the
Yes, yes.
Why are we doing function parentheses and not the for operation itself?
Okay, we are calculating something that's executable, right? So you can think about the 4 keyword over here indicating the 3 components that we have to consider. So the for itself is not really executable. It's indicating we need to consider part number 1, part number 2, and in this case, part number 3 is missing, so we don't consider that. That's what's happening. Yes, final one. Go ahead.
If we were in the progress, would it be 3n or 2n still? Because like, what I was asking is, does that first field where it's setting I equals something
Yep.
get updated?
Very good, very good. To answer your question, let me say this. Let's say if I++ is over here, how should we calculate it? Number 1, when I talk about line number 6, the meaning will just be the same. You just different place you put, just different syntax. And if I ever put any progress part over here, think about this progress part. When will the progress part be executed for the very first time? Is it going to be executed when you first enter the loop? Should be at the end of the first iteration. Agree? That's the first time. Good. If you remember that principle, then you'll be fine. Okay. Execute it the first time, if any. If any, at the end of the first iteration. And I try to be very careful with my words when I say if any. Why? In some cases, which we might see later when we implement certain data structure, in some boundary cases, you may not even enter the loop for the very first iteration, meaning that the state condition there evaluate to false right away. There will be some boundary cases like this you have to pay attention to. Okay, you might see that later. All right, we are good with this. Let's move on. I think the rest will be quite straightforward, but let's be careful. Now, can I point to you, if you don't mind? What's your name? Kyotr. I remember you made a slight mistake for this one here. Would you like to try this one here? How many primitive operations do we have? Give it a try. You can think aloud. That's okay.
Okay, so first we know that lines 4 to 6, it's done n minus 1 times, right? But that specific line, right? Every time that line runs, it's done 2 times because in that there's 2 primitive operations versus the indexing instead of the comparison.
Yes. So do you think the answer should be 2?
Well, no, not 2 times because it repeats for the
Ah, very good. So now you did correct your mistake. I like it. Yes. Yes. Okay, very good. Thank you. I got you. All right, guys, be careful. Yeah, I'll just continue to complete your answer. So here, if you see each iteration, you're going to have two primitive operations, right? You're going to have, number one, over here, the relational operation. Number two, the array indexing over here, right? Two. But how many iterations do we have? M minus 1, as we said before. So it's going to be, I'll put it here, m minus 1 iteration multiplied by 2, right? The 2 here correspond to indexing and greater than. All right, we can speed up. What about this one here? Hopefully you guys will be convinced this one here will just be, we still got the same number of iterations multiplied by array indexing, variable assignments, also 2, right? You guys might have a question now. Depending on the array structure, sometimes this may not be true. Sometimes it may be false, right? But as I said before, when you analyze or count primitive operation, we don't really consider the logic too much. We only try to calculate line by line so that we can get the absolute worst case. Maybe worse than necessary, let's put it that way, but that's okay. Question?
Shouldn't the if statement, similarly to like the for loop thing that we did before, shouldn't line 4 be ran one more time than line 5? Right? Shouldn't we see that line 4 when it's
No. Line number 4 and line number 5, they are part of the loop body. So that means every time if you actually execute the loop for one more iteration, this line will only be executed for one more time. Similarly, this line will also be executed for one more time. And in this case, we don't really consider the fact that if this evaluates to false in certain iteration, we don't execute this. We don't consider that. We're considering the absolute worst case. Okay, good. Any question? Ferris, did you have a question? Yeah. Only the absolute, yeah. Yeah, as I said before, it might be worse than necessary, but that's okay. Okay. All right, guys, what about this one, please? Final one. Definitely n minus 1 iterations. How many primitive operations for each iteration? 1 or 2? 2, okay. Yeah. So for your information, I'm pretty sure you know. If you don't mind, I'm going to write it down. This corresponds to I is assigned to I plus 1. So you got arithmetic and assignments, so 2. Okay, so I'm going to put 2 over here. And finally, outside the loop, we have this. We got a single return statement. So now be careful, because this one over here contains nothing that's more, let me say it again. This one here, if it turns out to be, for example, I plus 1, just say for example, in that way, you have to really consider the return and also the plus, so that'll be 2. But now it's only a single variable, so you don't need to worry, just a return itself, so it's 1, okay? So that will be just 1. And what should you do now? You want to add it up, okay? I'm going to highlight what you need to write down. You want to add up. Do I have any color I haven't used? How about yellow? Here, 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 and here. Right? I'll write it down here. 2 plus n plus 1 plus, so now you can see n minus 1, we got the same, 1, 2, 3, 3 times, right? So let me be a little bit lazy here. N minus 1 times 6 plus 1. All right? I'm pretty sure you guys know how to do this, right? And if you check the slides, seven n minus 2. And let me make a concluding remark. In the test or in the exam, given an algorithm, to really figure out its running time, there are 2 possibilities I might ask you. Number 1, if I say, calculate the number of primitive operations, you have to be 100% precise. For example, if your answer would be 7n minus 1 or 7n minus 3, that's not correct. All right? Okay, the second kind of question I might ask you is to approximate the running time. That'll be a different story. In this case, when you do the calculation, it can be a little bit informed, I shouldn't say informed, a little bit rushed, a little bit not so careful. In that case, missing 1 or missing 2, as long as the highest power of n is maintained correctly, you'll be okay. Okay, that's something I want to mention right away.
So when you're approximating, we can't rush it, but we still have to follow the same process, so we couldn't just,
Yeah.
look.
You will, yeah. So you don't necessarily have to calculate the primitive operations so carefully, but I'll show you a way to really figure that out. We'll see later. Yeah. But if you want to calculate precisely, that's what you got to do. Okay.
So for example, on the test, if you said 7n minus 3, would that be like the 0 or would you be proper?
That's a good question. If the question itself is simply leave it blank for you to say, okay, tell me the number of primitive operation. There's only just a blank answer, right? In that case, if you answer that wrong, you get 0. On the other hand, in the exam, we'll give you a very large box for you to show your steps. In that way, if we see you only make some tiny mistake in the middle, you get partial marks. It depends how we ask. Yeah. Guys, am I right? We still have time, right? Okay, I want to make sure. Okay. All right, any question? Are we okay? Okay. And you guys definitely got an idea. I will give you some exercise over here. You can do on your own. This will be just another example over here. I'll show to you. Okay. I'll leave this page clean for you. You can feel free to print it out and can do the exercise on your own. I'll suggest do it right away, maybe after class, just as you are still fresh about the result. Exercise for you. And for those of you who may still not feel very comfortable about how this can be calculated, I would suggest try to answer question 1, 2, and 3 first. That will help you. All right? If you got trouble, my office hour this afternoon, speak to me. All right? You want to sort it out earlier rather than later. Good. Okay, and the next one that we want to talk about would be from absolute running time to relative running time. Let me go a little bit more slides, and then we can take a very short break, and then we can continue. Okay, I think that was a nice continuous block to talk about. Okay, right. So now we want to say, what's really the use of counting primitive operations over here? How is that going to help? Compare with when we did before we measured the elapsed time for the algorithm. That's something I want to address in this slide. And please pay attention to what's really being said in this slide. That one there really tells you how you can transition from experimental approach to the mathematical approach. Okay? There will be a little bit equation here. Don't be too scared. It's actually rather easy. Okay? Let's take a look. Each primitive operation that we consider takes the same time, depending on the execution environments. What do I mean? Let me put it over here. Okay. For example, so we're now talking about going from from absolute running time, which we did last time, to relative running time. Okay. First of all, let me also be consistent with the color I'm using. Okay, red. Okay. When we talk about the t, okay, let's understand this little t over here is referring to the exact time taken to execute a primitive operation. And the t here may be different depending on which operating system you're using. Or even within the operating system, it depends on what the workload is at the moment. For example, I want you to understand this t very nicely. For example, let's say in your Mac M1, t could be, I'm making this up, maybe 2 milliseconds. Let's say you have the Mac I'm using here, it was back in 2014, right? It might take longer, I don't know. Right? I'm just saying that depending on the architecture of your computer or the working environments, the t may be different. but it should be a constant, rather small. The idea would be we want to express the absolute running time in terms of t. And then we can conclude that t itself can really be somehow factored out in order for us to do some meaningful comparison. Though t here is not really necessary for our purpose. That's the conclusion I'm going to make. But before that, let's go over a little bit more slides. So the number of primitive operations required by an algorithm should be proportional to its actual running time. What do I mean? Something like this. Remember that findMax we just did, right? If you actually got 7n minus 2, okay? So the findMax that we just did, the findMax contains 7n minus 2 primitive operations, right? For example, if I'm talking about executing this findMax on Mac M1, how long would it take? 7n minus 2 multiplied by 2, right? Of course, n here also depends on how large the array is. Oh, one more thing I want to just make sure you, maybe I didn't quite mention explicitly. I want you guys to see. Beg your pardon, very quick distraction. Here, in the findMax, if you look at the parameter, we have one array and also n. N here is a very common variable for denoting the size of the array. So let me show you one example right away. Sorry, I forgot to mention. Let's say we have some integer array A. Oh, guys, you should have told me earlier, right? There we go. All right, guys, don't be shy. Shout on me if I forgot. Don't shout me in general, but shout on me if I forgot, okay? Here, what did I say? What I tried to say was, here, when I say I got findMax over here contains 7n minus 2 primitive operation, right? I want to just have a little bit of distraction over here to talk about how you can use the n over here. So findMax over here takes an array. Let's say the array looks like this. 2, 3, 4, 5. Doesn't matter. So the length will be 4. So the way you use the findMax is like this. You will call findMax, and then you pass the a, and then you say a.length. Right? So a.length over here is really correspond to n. What I could have done, you might be wondering, would be to replace every occurrence of n here, for example, by a.length. That's also possible. But n here, you just got to remember, if you read any standard textbook or any other online lecture, they always use n to denote the size of the input. So that's why I want to introduce n as well. Right? That's something I want to clarify. Okay? Let me go back. And let's definitely finish that slide, right? Please, hopefully I got enough time. findMax contains 7n minus 2, and the n here is the size of the array. Let me remind you. N here is the size of input array. All right, so now if we are going to execute findMax in this particular setup, it's going to be 2 times 7n minus 2. Of course, n also is some input size you got to replace, right? You can calculate the precise time, absolute time. Similarly, what about running this algorithm on this Mac 14? You got to use 4 to multiply by this number here, right? You see my point? Okay. But is it really necessary to consider t always? Not really. Why do I mean? Let's take a look. So that's what I just said, right? Let's say we have 2 algorithms. Let's say we got algorithm number 1 and number 2. Algorithm number 1, algorithm number 2. 7n minus 2, let me just recall, 10n plus 3. Okay? Number of primitive operations exactly over here. This is number of primitive operations. This is also the number of primitive operations, right? How do we calculate the absolute time? Multiply this by t. Multiply this by t. So the whole thing over here is the absolute time. And the thing over here is also the absolute time. All right. Of course, in order for me to decide which one might be more efficient, I can definitely consider the evaluation of the precise t over here could be either this or this, right? And then compare them. But is it really necessary? In order for me to see whether this is more efficient or this is more efficient, I don't need to consider t. I don't need to. Only compare this. So that's why relative efficiency is more convenient to calculate. That's the way we're going to do. We don't really have to consider this particular t, which depends on the operating system you're running. So in this course, from now on, we're going to focus on just about approximating or precisely calculating the primitive operations. All right? So if you move on to the slides over here, you will see like that. So we only consider this by disregarding the t, because t itself will be somehow, it can be just factored out anyway. Right? And the conclusion will be to determine the time efficiency. Now in this course, we're going to only focus on their number of primitive operations. And now we can either precisely count how many, which we did, or we can approximate it using big O. Any question so far? Yes.
Questions of attention. So like the relative that we have there is the worst case scenario, right?
Mm-hmm.
Oftentimes when I like look online and see and like look at algorithms, they also give a best case. I was thinking like, what would be the point of determining that?
Yeah. Yep. As I said before, in this course, we're actually going to focus on worst case scenario, because that tells you what will be the worst scenario for your algorithm to be executed. So if you compare the worst case for one algorithm and the worst case for another algorithm, you can easily compare. So best case scenario is not the one to compare, because for many algorithms, their best case might just be constant. Let's say for merge sort. Merge sort itself is quite complicated, but its base case is incredibly simple. It just returns true or return false, depending on whether the array contains certain number, right? In that way, comparing two sorting algorithms where the best case are simply constant is not meaningful, because you're not really considering the more sophisticated scenario of the input. All right? Yeah. So we only consider worst case. Barrett's. Mm-hmm. Very good. Very good. Yeah, so thinking this way. Yeah. So each individual primitive operation is very cheap. That's true. But when you aggregate different primitive operations together, they might aggregate to a certain number that depends on the size of the input. In that case, you cannot ignore them. For example, if somehow for the algorithm, okay, I'm here. So for the algorithm, if the number of primitive operations you calculate would just be, for example, some constant 52. In that case, it's very good. That means the algorithm always take 52. On the other hand, if you say the number of primitive operation will be, let's say, 2n. So this one here is not the same. If you compare 52 versus 2n, they are completely different in the following sense. This one here, doesn't matter how large the input size is, it will always be 52. This one here, if the input size is 1, then 2 primitive operation. If input size is 5, it will be 10 primitive operation. If it is 100, it's 200 primitive operation. It depends on the input size. So that's the difference. Yes, it kind of depends on the action, the function itself, which we'll talk about. All right, let me write down. I'll take more questions. That's okay. Let me write down here. So this 52 over here is constant despite input size, always 52. And this one here is, we call linear on the input size. The larger the input, the larger number of primitive operations it will involve, because potentially there might be a loop to really loop over the array. Okay, question?
One algorithm to be a lot better than another in terms of the worst case scenario, but due to
You're asking very good question here. Is it possible to say, based on the worst case scenario, we might choose this algorithm, but maybe on average, maybe the other one might perform better. I wouldn't say that's impossible, but don't worry, for this course, we focus more on the worst case, but that's the simplest one to calculate in some way. Average case, which I'll mention in another slide, it normally requires the manipulation of some probability, like expected value. Do you guys remember what you learned in 2030, right? I mean the math. You got to calculate the expected value of certain, like a dice, right? So when you calculate for average case, you have to calculate for expected value. I think I do have some nice exercise I really hope I can do together with you in class. Otherwise, I'll give you the video to watch. Okay? How about I just do one more sketch? Done, if you don't mind. Let me take 1 or 2 minutes. You guys can tell me what you think intuitively. I know I'm running over time. Give me 1 minute or 2. Tell me what you think intuitively. Let's say we have a problem here to resize array. Let's say we want to keep adding elements into an array. That's the problem. Back in 1022 and 2030, right? You always declare some fixed size of the array, let's say 100 elements. Once you have stored already 100 elements, you say typically, okay, that's enough. That's usually the assumption you can make. In this course, you may not have to. Okay, let's say this. I got an array over here with certain length over here. What if I want to add, we already occupy the entire space of the array. Now I want to add one more, right? What will be the strategy for growing the size of the array? Oh, don't worry, I'm going to answer that myself. Yeah, it's a rhetorical question. Yeah, you don't need to answer. Yeah, not just yet. Okay, there are 2 ways. Number 1 is called a fixed growth. Okay, sorry, I forgot a precise term, but that's pretty much accurate. Fixed growth approach. In which case, given n over here that's already occupied, I will just add a fixed size only. And that fixed size can be some constant c. That'll be the fixed size. Every time I fill up the array, I just add that particular one with c. Okay? What about number 2? You may have heard about this before. It's called doubling. Let's say if I got initial array over here, that's already occupied. If I want to grow, I'm not going to grow just by some fixed amount. I'm going to double the size of the array. Okay, every time, maybe from 10 to 20 to 22, 40, and etc. Intuitively, which one is more efficient to you? Or you can take a guess. 1 or 2? You think 1? Okay. Okay, 1 and 2. Okay, I guess maybe some of you think 1, some of you think 2. Time efficiency. Overall, which one should be more efficient? Okay, it turns out. I'm glad you answered 1 because the answer is 2. No way? Okay, I'll try to convince you mathematically later. Okay, so let me just make a 30 seconds remark and then I'll definitely let you go. We have to justify this by using something so-called amortized analysis. Meaning that we're going to calculate the average case. It turns out the average case for doubling turns out to be more efficient than this one. It turns out. And I will try to see if I can discuss this in the class. If not, at the bottom line, I do have some very good quality video to walk you through the process. Either way. But we haven't got there yet. Guys, thank you so much for your patience. For those of you who celebrate for New Year this coming weekend, Happy New Year. Otherwise, I'll see you on Monday.